While polynomials can in principle have many variables in them, x, y, z, as many as you like, binomials only have two, and typically we call those x and y. Now suppose you want to raise your binomial, x plus y, say, to some power, so x plus y squared perhaps, and then expand it. Now if the power is small enough, 2 or 3, so squaring it or cubing it, we can do that reasonably quickly. But as the power gets bigger and we get more and more brackets, while we can still do it, it starts taking a very long time. Is there a better way of going about this? Instead of just blindly going through the routine of multiplying one bracket by another, let's look for some patterns which might really shortcut the process for us. You have probably come across Pascal's triangle before, with all its quite amazing patterns. And here comes another remarkable thing about this pattern I want to show you. First of all, look closely at the coefficients of the x's and y's when I have raised the binomial x plus y to increasing powers. So to the power of 0, it's just a 1. To the power of 1, so n here is 1. The coefficients I've written out fully are 1 and 1. When I raise x plus y to the power of 2, the coefficients are now 1, 2, 1. And now as I call out the coefficients of this next expansion when I'm raising it to the power of 3, you just glance down at Pascal's triangle below. The coefficient here is 1, 3, 3, 1. What do you see? We are trying to find what would happen if we expand x plus y to the n. And we don't want to be doing that bracket by bracket, but now Pascal's triangle is giving us a quick way into this, because this triangle will quickly give us the coefficients of any binomial expansion we choose to do. That's fantastic. But even that will get a bit slow if n gets too large. Is there a way we can use a little bit of algebra to write down the general term of any expansion at all? Well, yes, there is. And now we're going to have a look at what that is. But first we need to revise a little bit of work we've seen before, factorials and combinations. NCR is the number of different ways of selecting R objects from N. And factorial 0 is defined to be 1, which is very nice and stops us having lots of zeros on the denominator. So now I've written down the values of a sequence of combinations in an orderly way and set it out like this so that you can see something else remarkable. Look at those blue numbers, which are just the values of those different NCRs, but look at them. And look at our Pascal's triangle. Isn't that amazing? So Pascal's triangle, and therefore the coefficients of any binomial expansion, can be written as combinations. And this is the basis of the wonderful Binomial Theorem, which I have written here in its simplest form. The important points I want you to understand are the sequence of combinations that go with the different powers of x and y, and secondly, to know and be able to use the general term. That's really important. In the next video, I will extend this a little to any linear combination of x and y, such as ax plus by all to the n. See where the a's and the b's fit into the general term, and then use all this to solve many different types of problems involving binomial expansions.